stoichiometry and chapter 9 and got into sort of basic stoichiometry sort of problems and really the steps that you need to follow. And really for a basic stoichiometry sort of problem, there's kind of four basic steps. You want to always make sure you have a balanced equation. So again, if the equation is balanced, you're good to go. If not, then you definitely want to make sure it is balanced. Second, pretty much whatever they give you, you want to convert to grams, and then they'll take those grams and convert it to moles. Again, the molar mass from the periodic table is what we use to do that, grams per mole. And then really the third step is the stoichiometry step, and that is the mole-to-mole relationship. So as we talked about from a balanced equation, you could take all the coefficients as the moles of everybody, and you basically can write some equalities, relationships from the equation. So we can say for every 2 moles of A, you got to throw in there 3 moles of B, for example. And from that equality, we could write 2 conversion factors, 2 moles of A over 3 moles of B. Our 3 moles of B is 2 moles of A. And once again, there's a lot of other sort of relationship and convergence factors we could get from this equation. As we talked about, you will not use all of them. You'll just use whichever one that you need. And the purpose of stoichiometry is just that you have a piece of information about somebody in the equation, but you're really interested in somebody else in the equation, and you need a conversion factor to go from the thing that you were given to the thing in the equation that you're interested in, and that's what it's referred to as the mole-to-mole relationship. So you'd go to the equation, do the mole-to-mole relationship, again from the balanced equation. And then at that point, you should always be in moles after you do the third step. And really, it really does depend on the problem, but it oftentimes will ask you to convert those moles into some other unit. I would say, again, grams is a very common sort of bless you ending to the conversion at the end, where you may use molar mass, but you really could be asked for any type of unit at the end. But again, probably a lot of times you're going to kind of end up in grams maybe. And once again, that's going to be the molar mass that's going to allow you to go backwards to it. So it really is these four steps in order. You don't want us to go backwards. If something's done for you, just go forward. Any questions on that there? So let's take a look at one here. And let's look at this one together, just kind of go through those steps. So lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We want to know how many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water. So the first step that we need to do is, in this case, we are not given the equation. So we do need to write the equation. A reminder that when you're writing chemical equations, you don't want to worry about the balancing part first. You want to just get all the proper formulas down. So lithium metal is just Li, reacts with water, which is H2O, to form hydrogen gas. Remember, hydrogen gas is a diatomic, and lithium hydroxide here, lithium plus 1, hydroxide minus 1, gives you something like this. At this point, once you have all the proper formulas down, then you can proceed to do your balancing. And at that point, I think you're just going to need perhaps a 2 there, 2, and a 2 there to balance. So we got 2 lithiums on each side, got 4 hydrogens on the left, 4 on the right, 2 oxygens on the left, and 2 on the right. So we are balanced in this particular case. And again, proper formulas, then balancing with coefficients. Now that we've done that, we want to kind of think about what was given to us, which is we want to know how many moles of H2, so we eventually want to get here, but we are starting with 5.32 moles of Li. So the second step along the way is to convert whatever they gave us into moles. So we want to convert to moles. And this is already done, so we don't actually have to do that. So again, don't undo it and redo it because it's already in moles. Now that it is in moles, now we could actually do the stoichiometry part, which is our mole to mole relationship. And again, we're going to go to the balanced equation, and we're looking at, again, the two things we're interested in. Always one of the things you're interested in is what they gave you, and what you're trying to find should be the other thing that you're interested in. Really, in this problem, we don't have to worry about any other relationship other than those two. And from the equation, we could see that for every 2 moles of lithium, which once again is just the coefficient, we will get out 1 mole of hydrogen, which once again, also just the coefficient there. This again does give us an option of 2 conversion factors, 2 moles of lithium, 1 mole of H2, or 1 mole of H2 and 2 moles of lithium. So starting with our number that's already in moles, which is 5.32 moles of lithium. Just going to do a dimensional analysis to keep it simple. Opposites cancel. So lithium's up on top, so I do need lithium on the bottom, which would mean I would want to use a conversion factor there on the right. 1 mole of H2, 2 moles of lithium. Once again, like normal dimensional analysis, we're multiplying and dividing. The moles are going to cancel. And that's going to basically get us 5.32 divided by 2. And that's going to get us 2.66 moles of H2. In this particular problem, that is actually what we're looking for, which is how many moles. We actually do not need to do step number 4, is really not needed in this case. If we did want to convert this into grams, we would need at this point the molar mass of H2, and we could use that to convert it to grams, but obviously in this case, we were not asked to do so. Any questions on those steps there? All right, so let's take a look here. Thank you. So why don't you try one here? We're gonna do the exact same equation or reaction, but in this case, we're starting with 81.75 grams of lithium, and we want to know how many grams of hydrogen would we produce. So lithium 6.941, hydrogen 1.008. All right, so take a few moments there, follow the 4 steps, and see what you end up with. Again, balance the equation, convert to moles, mole to mole relationship, and mole to some other unit. All right, so take a moment there, see what you come up with. Okay, so let's take a look at this. So again, we want to follow the same 4 steps. This basic stoichiometry problem. We need to balance the equation, so that's already done for us as we did last time. Step number 2, we want to take whatever they gave us, which in this case was 81.75 grams of lithium, and we're looking for how many grams of hydrogen. We want to take whatever they gave us and convert it to moles, which we do need to do in this case since it's in grams. So we'll go with step number 2 there, which is we're going to convert to moles. And in this case, we'll take 81.75 grams of lithium. We would go to the periodic table there and find the molar mass of lithium. Again, grams are going to go on the bottom here to cancel out. And moles of lithium will go up on top. Again, these guys are going to cancel. That's going to get us here 81.75 divided by 6.941. You guys are like a, come here, 11.78 moles of lithium in this case. So I did first one, did second. Now we're ready to do kind of our stoichiometry, which again, we're going to look at the equation. We're going to find the relationship between the two things that we're interested in. And in this case, happens to be the same relationship that we saw on the first part of this problem. So again, from the equation, our mole to mole relationship is 2 moles of lithium gives us 1 mole of H2. Again, coefficients is where the numbers come from. That obviously gives us our two conversion factors that we could use, and we'll continue on with our number here, 11.78 moles of lithium. Again, we want to get rid of lithium, so lithium does need to go on the bottom when we use it as a conversion factor, and the 1 mole of hydrogen up on top. Again, moles of lithium going to cancel, then divide by 2. I'm actually using the whole number in my calculator, not the rounded number, so I get something like 5.8. I call it 889 moles of hydrogen. So that takes care of that step right there. At this point, if we were looking for moles like we were in the first problem, we would be done. But here we are looking for grams. So we do need to do step number 4 in this case. It's important to remember we're now at H2 and not lithium, which means we do need to calculate the molar mass of H2, 2 times 1.008 from the periodic table, 2.016 grams per mole. That's going to be used as a conversion factor. So taking our number there, 5.889 moles of H2. Moles going to go on the bottom, so they cancel. The grams up on top. These guys cancel. And that's going to get us here 2.016. We could pop it in there. About 11.87 grams of H2 would be produced in this case. First off, any questions on this step? As we talked about last time, you do not need to get an answer in between. You could just roll from conversion to conversion and get a final answer at the end, which is perfectly fine if you like to do it that way. This, by the way, means that if you put in there 81.75 grams of lithium into this reaction, everything went perfect, no side reactions, you weren't a klutz and spilled anything on the floor. You should, in theory, get out 11.87 grams of H2. This is what is known as the theoretical yield. It's like your maximum amount of product, your theoretical yield that you should actually produce in this case. A yield is a product, so you can only call it a theoretical yield if it is a product that you basically calculated. Any questions on those there? At the very end, you're talking? Sure, you're talking about the second part of it, the second step? Yeah. So the first one, it was given to us in moles. This one is given to us as grams. So if you're talking about this step, then that's why we had to convert it into moles. No, you gotta go in that order. The only time you could jump to step 3 is if it was already done for you, like it was on the first one. Yep. It should always go definitely in this order. And like I said, like just only if something was done, go forward. Yeah. Other questions? Go. All right, so let's see. That's what we just did. All right, so why don't you give this one a go? If 765 grams of C6H12O6 is consumed by the body, what is the mass of CO2? So basically, what is the grams of CO2 here? Give you some numbers, 12.01 for carbon, oxygen 16, hydrogen 1.008. All right, take a few moments. Again, go through the same 4 steps in order. See what you end up with. Okay, so let's take a look, see how you're doing. So again, we're going to always try and follow the same 4 steps here when you have just a basic stoichiometry problem. And here we're given 765 grams of our C6H12O6. We're looking for how many grams of CO2. So first step is balanced equation, which looks like it is balanced, so that's good. Second step is convert to moles. So we do need to do that step, as obviously the only number given to us is in grams. So we do need to get the molar mass of C6H12O6. So that is 6 times 12.01 for the carbons, plus 12 times 1.008 for our hydrogens, and 6 times 16 there for our oxygens. That's going to give us a molar mass here of 180.2, I believe, grams per mole. So again, that is our conversion factor from the periodic table that we use to convert to moles. So we'll take 765 grams of C6H12O6 and we'll convert it into moles using that molar mass. We'll go 180.2 grams per mole at this point. And again, if you want to get an answer, you can at this point, or you can just continue on with the calculation. It's completely up to you. If you do get an answer, as we talked about before, try not to round too much along the way. I'm going to actually on this one just kind of continue on with the calculation steps here. So really, if I stop my calculation right at this point, I have converted our grams of C6H12O6 into moles. And really, the whole purpose of doing this step here is to get everybody into the right units to do the stoichiometry, because the stoichiometry relationship is a mole to mole relationship. You have to have everybody in moles at this point. So the third step here is that mole to mole relationship. And again, we're going to go through the equation and find our two things we're interested in. Obviously, that is the C6H12O6, and that is the CO2 in this case. And from the equation, we can see for every 1 mole of C6H12O6, we get 6 moles of CO2. So continuing on here in just a one calculation move, we're going to go with moles of our C6H12O6 on bottom so that they cancel, and our 6 moles of CO2 up on top. Again, we're multiplying and dividing still, so these guys are going to cancel, and that was our third step right there. That's really the stoichiometry step at this point. Again, if I was looking for my answer in moles of CO2, I would be done at this point. I could just get the answer, obviously, and that would be the correct answer. But again, we're not looking for moles. We are looking for grams. So we do have to do our fourth step, which is take those moles to some other unit. And again, at this point, we do want to remember that we have now used stoichiometry to convert to CO2. So when we use the molar mass, we do have to calculate the molar mass for the correct thing, which in this case is CO2. And that would get us 12.01 for our carbon, plus 2 times 16 there for our oxygens. It's going to give us a 4401 grams per mole, which again, we're going to use in our conversion factor. Again, written dimensional analysis, we see moles of CO2 up on top. We want to get rid of the moles of CO2, so we got to go moles of CO2 on the bottom and grams of CO2 up on top. Again, that's going to cancel out. And now here we will end up with basically 765 times 6 times 4401 hit equals divided by 180.2. Going to get us about 1,121 grams of CO2. In this case, we're probably looking at only 3 significant figures based off of the only number given to us. So about 1,120 grams of CO2. Once again, CO2 is a product. So this would be known again as the theoretical yield in this case. And again, step number 4 right there, basically. So as I mentioned before, if you want to kind of do it all in one calculation, you can. You just want to set it up with dimensional analysis. Again, opposites canceling Or you could do like we did previously, which again is sort of get an answer after each step. Just try not to round, like I mentioned a second ago, till the end. Any questions on that there? Yeah. All right. Continue on here. So I think that's what we just did. So just pop that up there. Uh, all right. So why don't you give this one a go? How many grams of cisplatin, whose molar mass is 300.1 grams per mole, can be obtained from starting with 0.7752 grams of our K2PtCl4 molar mass from the periodic table, 415.1 grams per mole. So they're nice to give you the molar mass. So continue on there, same 4 steps. Give it a go. Okay, let's take a look and see. Again, always just going to follow our 4 steps. So once again, I see some coefficients in that scary looking equation and it looks balanced in that case. I'm going to go with that. They did give us that we're starting in this case with 0.7752 grams. And in this case, we're looking for how many grams of our product. So we do need to do our second step, which is take whatever they gave us and convert it into moles. So step number 2, we're going to take our 0.7752 grams. We're going to convert it into moles. Nice thing about this problem was they already gave you the molar mass. So if they did not, you would have to go to the periodic table and obviously add it up yourself, which in most cases you will have to do. So we do want to get rid of grams. So we are going to put the grams on the bottom in this case. So that we end up with moles. And again, the purpose of this first step is to get everybody into moles so that we can do the stoichiometry part of it. Once again, here I'm just going to do it all in one calculation. So at this point, the grams are going to cancel, and we would then have moles of this guy here. That means we're ready to do our stoichiometry step, which is the mole-to-mole relationship. And again, from the equation, we see that for every 1 mole of K2PtCl4, we get 1 mole of our product as well. So a 1-to-1 relationship is always good. And again, we're going to set it up. Opposites cancel. So we do want to get rid of this guy. And we do want to end up with this guy up on top so that we have the right thing there. So 1 mole of what we're looking for up on top. I squeeze it in there. And 1 mole of what we started with there on the bottom there. Again, multiplying and dividing, these guys are going to cancel. Once again, if I was looking for moles, I could definitely get an answer at this point and I would be done. But we are looking for grams. So we do have to do the last step, which is take our moles to some other unit. Once again, in this problem, they actually gave you the molar mass. If they did not, again, you would have to go calculate it yourself from the periodic table. So using the molar mass that was provided for us, we want moles to cancel. So moles of our product here. And grams, which was 300.1 grams. Again, the moles are going to cancel, and that's going to get us here basically 0.775 times 300.1 divided by 415.1. Going to get us about a 0.5603. 0.5603 grams of our product here. Once again, because this is a product and we starting amount was given to us, this again would be our theoretical yield in this case. Again, same 4 steps. Step 1, balance equation. Step 2, convert to moles. Step 3, mole-to-mole relationship. Step 4, moles to grams in this case using the molar mass. Any questions on any of those steps there? No? So these are basic stoichiometry problems, and the reason I say they're basic stoichiometry problems is typically in a basic stoichiometry problem, you're just given information about one thing in the equation. So if you have any problem where you're just given one thing in the equation, you should follow these 4 steps. And again, that will get you to your answer. As we also talked about before, a reminder that in all these problems that we just did, we did do the stoichiometry across the arrow, but you do not have to cross the arrow to do stoichiometry. You can do this type of calculation between the two reactants. You can do it between the two products. You can go products back to reactants. So you can really use these steps for anybody in the equation and relate them through their stoichiometry. Any questions on that there? Yeah. So the next thing we're going to talk about is a sort of progression of a stoichiometry problem, which is known as limiting reagents. And the idea behind limiting reagents is when a reaction takes place, there's always some reactant that actually gets used up first. So there is a reactant that gets used up first, and that's what's known as the limiting reagent. And there's a reagent or reactant that you have plenty of, and you actually have some left over when the reaction is done, and that is what is known as the excess reagent. So you basically have two types of reactants, the limiting reagent and the excess reagent. Limiting reagent gets used up first. Excess reagent you have plenty of in that reaction, and it will still be there when it's over, and you'll have some left over. Why is the limiting reagent really important? Limiting reagent, excess reagent. It is the limiting reagent that is really the most important thing, because if you think about it for this just simple basic idea here, if you have A plus B going to make A and B, and let's just say, for example, that A is my limiting reagent and B is my excess reagent. Now, the problem with this is as soon as I run out of A, there is no possible way for me to make any more product, right? Because you need an A and a B in this simple example to make a product. And if you run out of A, there's no possible way you're going to be able to make any more products. So between the limiting reagent and the excess reagent, the limiting reagent is the most important one. It determines how much product you can make. So this is the most important. It determines how much product you can make. Because once it is used up, there is no possible way for you to make any more product as a result of it. And again, that's why we always do calculations of how much product we would make based off of the limiting reagent, because once it's gone, no chance to make any more products. Now, the excess reagent is the reagent that you have plenty of, and you'll have some left over at the end of the reaction. A lot of times you're sometimes asked to calculate how much of the excess reagent you may actually have left over. That's something that's a common sort of question that is asked. Limiting reagent should go out to zero, basically. Excess reagent, you'll have some left over when the reaction is done. Any questions on that? How do you know it's a limiting reagent problem versus a sort of just basic stoichiometry problem? The reason or the way that you could recognize it's a limiting reagent problem is you're given information about both reactants. So if you have enough information about both reactants, that you could calculate moles. So if you see in a problem there's enough information for you to calculate the moles of each reactant, it is a limiting reagent problem. So if you think about the examples we did previously, we were only given like one piece of information about somebody. But if you're given both reactants, enough information to get the moles of both reactants, it is definitely a limiting reagent problem. You got to kind of figure out which one's the limiting reagent before you can figure out, how much product you produce. So if we were making sort of exercise buddies here, and we could see that we need one of each. So this one and this one makes a partner. This one and this one makes a partner. This one and this one makes a partner. We can see here, there is no chance at this point to make a guy and a girl partner, as we have now ran out of this guy over here. So that would mean in this example, this is our limiting reagent. This is our excess reagent in this example. And as I mentioned before, a very common sort of question is how much of your excess reagent is left over. In this example, you can see you could count. You have 2 left over. in this particular example. So these are very common sort of questions. Now, if we have this reaction here, and let's just say, for example, we could still do our normal stoichiometry relationships, which obviously there is 1 mole of sulfur reacts with 3 moles of fluorine and 1 mole of SF6. So let's just say, for example, we were given a problem where they told us we are starting with 4 moles of sulfur and we are starting with 20 moles of F2. So we're just going to kind of use that as our example. Now, there are a few different ways that you could do these type of problems, these limiting reagent problems. So we're going to talk about no problem. We're going to talk about one way to do it, and we'll talk about another very common way to do it. And you can kind of choose whichever way you want to do it. So the first way, and probably the way I'm just going to kind of mainly do it, is based off of what we just did, which is our basic stoichiometry problems. So when we have a limiting reagent type situation, we can still follow our basic steps of we're going to balance the equation. We're going to convert whatever they give us to moles. We're going to do our mole to mole relationship, and we're going to convert those moles to some other unit. So just like a basic stoichiometry problem, those are the steps we're going to follow. The difference is right around here at this step, between step number 2 and step number 3, we're going to actually figure out the limiting reagent. So we're going to figure out the limiting reagent. And by the way, when you do figure out the limiting reagent, it does need to be done through a calculation. You can't just like look at it and go, oh, that one has less moles, so that's like my limiting reagent. You actually have to do a calculation to figure out which one is the limiting reagent. You can't just magically choose one when you look at it. So in this particular case, and in most stoichiometry problems, regardless if they're basic problems or limiting reagent type problems, you can basically just follow the same kind of steps we've been talking about. So the first step obviously is we're going to balance our equation, which is done already. The second step is we're going to take whatever they gave us and convert to moles, which is already done for us, right? So we don't have to undo it. But very commonly, just like previously, you may have to take grams to moles, which is a very common thing. Now, when I look at this, I definitely have moles of each reactant. And because I have the moles of each reactant, or I could calculate the moles of each reactant, that is definitely how I know that this is a limiting reagent problem. So right there, that piece of information that I could get to moles of each reactant tells you you need to do the limiting reagent sort of step. So that's how you can recognize that you need to do it. So how do we do the limiting reagent step? So to determine the limiting reagent, you're basically just going to do a very simple stoichiometry calculation. And what sometimes helps people is you can look at these two here, and these are really your starting amounts, right, of each of those reactants. So this is how much you're starting with. So to figure out which one's the limiting reagent, we're going to do a simple stoichiometry calculation between the two reactants. And this is basically the question we're trying to figure out, which is, let's just say if I want to use up all of my sulfur, how much F2 is needed? So this is basically what we're trying to do with this calculation is to go, okay, I want to use up one of my reactants. How much of the other reactant is needed to do that? So let's do that calculation. If I am starting with 4 moles of sulfur, I could go to the equation and find the relationship between sulfur and the other reactant. And the other reactant and sulfur, the relationship is for every 1 mole of sulfur, I have 3 moles of F2, just like we do a basic stoichiometry relationship. So if I want to know how much fluorine is needed, I'm going to put the fluorine up on top. and the moles of sulfur on the bottom. So this is just like doing stoichiometry like we did previously. This is going to cancel out our moles, and that's going to tell us that we need 12 moles of F2 is needed. So 12 moles of F2 is needed to use up all of the sulfur we started with in this reaction. First off, any question on that calculation? Now, what do we do with that number? Well, I now have calculated that if I want to use up all my sulfur, I need to put in there 12 moles of fluorine. How many moles of fluorine did I start with? I'm going to take this number and compare it to how many moles of fluorine I started with, and I started with 20 moles. So I need 12. I started with 20. Do I have enough? I do. So because you have enough, that means that fluorine is going to be your excess reagent, and sulfur will be your limiting reagent. Any questions on that? So just to show you, and by all no means do you need to do necessarily both of these calculations, just to show you it doesn't matter which one you choose. So you could choose, for example, let's just say you want to know how much sulfur is needed to use up all the fluorine. So you could basically do the other calculation, and you could go, okay, I got 20 moles of fluorine I'm starting with, and if I want to use all of those up, I would still use my same relationship here. I would need my 3 moles of fluorine on the bottom and my 1 mole of sulfur up on top. And that would tell me that 20 divided by 3, 6.67 moles of sulfur is needed. Now, if I took the moles of sulfur needed and I compare it to how many moles of sulfur I'm starting with, do I have enough? I do not. I need 6.6 and I only have 4 to start with. I do not have enough. So that again tells me the sulfur is my limiting reagent and my fluorine is the excess reagent. So again, you do not need to do both of those calculations. You could just do one, but it doesn't really matter which one you choose. You want to do it with the first reagent to the second or the second to the first. It doesn't matter. They will tell you the same thing as in terms of which one's your limiting reagent, which one's your excess reagent. The good news is once you do one of those calculations, regardless of which one you end up with, your excess reagent or your limiting reagent, the opposite thing is happening to the other thing. So if you figured out what thing is our excess, then the other guy's your limiting. If you figured out the first guy's your limiting, then the next guy's your excess. So they are always together and opposites of each other. Any questions on that? It was like a problem, like we started with 4 moles and 20 moles. Like you and made up those numbers, like a problem example that we started with. Yeah. Other questions? So this, now that we figured out that in this case sulfur is our limiting reagent, we can then figure out really the rest of our steps. So now that we know that sulfur is our limiting reagent, you always want to do your product calculation based on the limiting reagent. So we would go back now that we know sulfur is our limiting reagent, and now we could actually do the problem. 4 moles of sulfur. We can now do the relationship between sulfur and our product here. And we can see from the equation, for every 1 mole of sulfur from the equation, we get 1 mole of SF6. And that would tell us we would produce 4 moles of SF6. That would be our third step, right? This, by the way, would be our theoretical yield in moles, right? So you could have a theoretical yield of moles. If we wanted to go to step number 4, we would then need the molar mass of SF6, which is 3207 grams per mole for sulfur, and fluorine is 19.6 plus 6 times 19 there for our fluorines. And that would get us here 32.07 plus 6 times 19. Gives us 146.1 grams per mole. And just like basic stoichiometry problems, we can now just kind of finish it up like normal using our limiting reagents starting amount. And we would end up with something in this case like 584 grams of SF6 would be produced. That would be our theoretical yield. So this is one way that you could do limiting reagent problems. You basically, in the middle of step number 2 and 3, you do just a simple little calculation between the two reactants to figure out how much of one you need to use up the other. First off, any questions on that? Yeah, 146.1, yeah. Now, like I said before, a very common question of that's usually asked as well is how much of your excess reagents left over. And based on doing this method, you sometimes can answer that pretty easily. We knew from our very first calculation here that the F2 was our excess reagent, and we calculated that you needed 12 moles of it to use up the other one. So we could figure out very much pretty quickly how much of the F2 is left over. We started with 20 moles of it in the problem. We needed 12 moles of it to use up our limiting reagent. And that would tell us that we have 8 moles of F2 left over at this point, which again, if you wanted to convert that to grams, you could use the molar mass of F2 and convert it to grams as well. So by doing this, if we did that first calculation for the limiting reagent, we can very easily and quickly determine, which one is the limiting, how much of the excess is left over. Yes, sir. Say it one more time. Are you going to ask? You don't. So it's just how much of your reactants are left over, basically. So excess reagents, limiting reagents, excess reagents, they're all reactants. So that's how much is just left over. So basically, you can think of it as like it's still in there, but it's just not. It has nothing to react with. So it's just in there. So in most of these cases, you're interested in how much product you're going to make and stuff like that. Other questions? So this is one way to do it. Another way that's very commonly taught is this, which is 40 and 20, right? So we had it was 4 moles, I think, right? And 20 moles of this guy. So the other method to do this is basically just do 2 separate stoichiometry problems. So basically what you would do is you would go, okay, I'm going to go 4 moles of sulfur. I'm going to do my mole to mole relationship between sulfur and my product. And that again is 1 mole of sulfur is 1 mole of SF6. And then I'm going to use the molar mass there, which I erased, which was 146.1, I think. 146.1 grams of SF6 is a mole of SF6. And that would get you 4 times 146.1, 584.4 grams of FF6. This is basically step 1, step 2, step 2, and step 3, and step 4. So just the basic stoichiometry steps that we did. Then what you would do is repeat. You take the other reagent and go, okay, I got 20 moles of F2. And I'm going to do the relationship now between F2, which is 3 moles of F2, and 1 mole of SF6. And basically do our 146.1 grams of FF6 and mole of FF6 here. Again, these are going to cancel. These are going to cancel. That's going to give us 20 times 146.1 divided by 3 going to get us 974 grams of SF6. So again, this is step number 2, step number 3, and step number 4. So the other approach that's very commonly taught these days is this approach where you basically just do two basic stoichiometry problems from each starting reactant, and the one that produces the smallest amount of product is your limiting reagent, and this would be your theoretical yield. And then basically you just ignored the other calculation and you did it for no reason. So you just kind of did it for no reason other than to help you determine that, and you just ignored the second calculation. So that's a very common way that it is sort of done this way, and it's perfectly fine if you would like to do that. You just do two separate calculations to the product. Whichever one produces the smallest is both your limiting reagent and your theoretical yield. Now, if you have this problem and you also were asked how much of the excess reagents left over, you would have to go back and do another calculation to figure that part out separate. But again, this is a perfectly fine method of doing it as well. There's like 3, 4 different ways you could kind of do these type of problems. Any questions on this method? So if you choose this method, basic 4 steps, start with each reactant to the product. And again, the one that makes the smallest amount of product is your limiting reagent and your theoretical yield. Any questions on that there? Question on limiting reagent type problems here. Okay. All right, I think we're late up there. We're going to